what's known as the cymatic properties of water, or in fact the cymatic properties of any kind of fluid. There were a number of experiments been done over the years that show how when water is transduced, or indeed any fluid is transduced, you get these interesting geometric patterns that are almost real-time physical visualizations of sound waves. These were originally explored by Gladney, who is sort of known as the father of acoustics, and he discovered that almost by accident, that when he drew a bow over his violin, when there was some dust sitting on it, it created these nodal patterns, these interesting geometric forms. And he went on to meticulously explore this phenomena, and it gave rise to a system known as Gladney Plates, which are these plates which you put different kinds of materials on, and then you subject them to sound, and that creates these geometric patterns. It was later then explored by Hans Jenny in the 60s, who basically did the same experiments again, and wrote a book on the subject, which has got these amazing colour pictures, and he also experimented with other substances like lycopodium powder. This is basically the basic setup. It's become a very fashionable experiment and art piece in its own right. Many artists have used this system. In this case, water is just put into loudspeakers, and a signal generator is used to basically transduce the water. And it has quite a long history. It goes back long before, in fact, computers. So hydroacoustic study is a hydrological narrative that unfolds in relationship to sound. So I wanted to use sound as a nourishing driving factor to generate different kinds of forms in this, what we call a rheological environment. I also was interested in maybe taking not such an obvious, and I was interested in creating a drama. So in some senses, the forms that I use have other aspects, and they have almost ghostly aspects, and they have forms that whereby the optical refraction and reflection creates a dramaturgy. The piece was actually made during an Optophonica lab residency, and it was originally made with a sound artist called Francisco Lopez, but I've gone on to produce my own sound to go with this work, so it's a standalone piece as well. Optophonica, as the name suggests, Opto and Phonica are very much interested in this, again, this cross-modal synesthetic marriage of sound and image, and the different ways that these two different perceptual phenomena can cross-relate and act upon each other. Another interest when producing this piece was what's known as the cymatic properties of water, or in fact the cymatic properties of any kind of fluid. There were a number of experiments been done over the years that show how when water is transduced, or indeed any fluid is transduced, you get these interesting geometric patterns that are almost real-time physical visualizations of sound waves. These were originally explored by Gladney, who is sort of known as the father of acoustics, and he discovered that almost by accident, that when he drew a bow over his violin, when there was some dust sitting on it, it created these nodal patterns, these interesting geometric forms. And he went on to meticulously explore this phenomena, and it gave rise to a system known as Gladney Plates, which are these plates which you put different kinds of materials on, and then you subject them to sound, and that creates these geometric patterns. It was later then explored by Hans Jenny in the 60s, who basically did the same experiments again, and wrote a book on the subject, which has got these amazing colour pictures, and he also experimented with other substances like lycopodium powder. This is basically the basic setup. It's become a very fashionable experiment and art piece in its own right. Many artists have used this system. In this case, water is just put into loudspeakers, and a signal generator is used to basically transduce the water. So as we move through the frequency bands from low to high, you'll see that you'll get much more complex patterns with the higher frequencies, and that matches up very much in the way that you would visualize sound on an oscilloscope, in the sense that you would have a much lower frequency with a much higher frequency. You would see more amount of wave phenomena within that band. Another component that I was interested in when I produced Hydroacoustic Study, and there were many different forms of optical effects that occur through water as a result of its turbulent flow, is that of acoustics, which is the way in which light passes through liquids, and the liquid acts as a lens, so that photons passing through the material, rather than strike in exactly the same places at the bottom of the material, would be refracted into the same spot, so you get these higher definitions of light in certain areas. I mean, and actually it comes from the Greek word to burn. This phenomena you will all have recognised when you look at the bottom of a swimming pool, and it's actually quite a hypnotic experience to look at this phenomena. It was first explored computationally by a guy called Josh Stamm in '96, and he found that you could approximate acoustics by using waveform algorithms and refraction algorithms. And it's actually really nearly impossible, obviously, to simulate this in computational terms, just because of the sheer amount of photons you'd have to model. The vast number would be impossible, so there's various ways of simulating this effect. Aside from liquid formations and water formations, I was also interested in bubbles, and more so given these bubbles a kind of extra phenomenon, an almost abiogenetic phenomenon, which is abiogenesis is the formation, or the idea of formations of living proto-cellular entities from inorganic materials, and it's a propositional explanation of how life might have formed on the planet. So these bubbles, they have textures which are possibly almost seen as lifelike, and I like the idea of these proto-cellular bubbles being nourished by sound. It was the means by which they were being transferred from this bubble-like state to a more cellular, lifelike state. So when I was referring to writings on optics in bubbles, I came across another few interesting phenomena. One of them is thin film interference, which is the explanation of how light is reflected from the upper and lower surfaces of bubbles. And during some of these refractions, there's often interference patterns are caused. This is the explanation of how, for example, you have iridescent rainbow effects on bubbles because of this interference pattern. In my piece, I'm purely using it as a form expression, because I've taken all the colour out. So there's still the optical effect of this interference, but the iridescent part of it is taken out. So this is a diagram of exactly what happens during thin film interference. For those of you who are interested, Robert Hooke was the first person to start to make annotations of this phenomena in as long ago as 1665 in micrographia. Yeah, another interesting effect of water and optical effects and the result of light passing onto it is known as a Fresnel effect. And this is an effect whereby the amount of perceivable reflection and specularity from the surface of the water is connected to the viewing angle. So, for example, if you look at the top of a swimming pool, you can often see to the bottom. There's not much light reflection coming from it. But if you look from any angle, a much more oblique angle, coming on from this angle, you tend to find that you can see less at the bottom, and there's a much more of this mirror-like specularity. So all of these phenomena go together in the algorithms that are used in the piece Hydroacoustic Study. I should also say that there's an interesting byproduct of Augustin Jean Fresnel's experiments, in that if you reverse the process, you end up with the Fresnel lens, which is the lens that are used in lighthouses. In fact, when I was coming in on the ferry from Holyhead, as I travelled in, I noticed there was a number of lighthouses coming in, and I must admit I did wonder. I know they're still being used, these Fresnel lenses. What they tend to do is they give out maximum amount of light from an oblique light source. by essentially reversing this effect. Again, there's kind of derivations and a diagram just to show how certain amounts of the light are reflected and certain amounts of light are passed through the water depending on the angle. So basically all these equations that I've been talking about and all these derivations are somehow put together in a computer program known as a shader, which is a very powerful program that actually runs on the GPU, actually runs on the graphics processing unit. So it's very efficient in terms of the way it works with today's modern computer hardware. So the other real important component, aside from these optical effects in the hydroacoustic study, is sound, and how to actually transform sound into movement and shape within this system. Essentially what hydroacoustic study does is it samples sound at a number of frames per second, how many frames I'm running the software at. In this case, it will be 30 frames a second. So every 30 frames a second, I look at the sound, and I look at the sound in many different ways. And then what I do is I use those readings, those parameters, to drive certain aspects. They might be textural aspects, they might be the surface of a bubble, or they may be a wave effect. And what I do is I use my own kind of artistic imagination together with my scientific studies of actually how sound does affect water in the real life, as it were. So the two areas of frequent analysis that is carried out is, the two sorts of sound analysis is, one is frequency analysis and one is amplitude analysis. With frequency analysis, I'm looking at all the frequencies, the prevalences of all the frequencies in each frame. So I would get up to 512 different values, probably 256 values for each channel, left and right. So I can see how much of each, if I split up all the frequencies into 512 bands, I can read exactly how much of each of those individual frequencies I'm getting. And this can be quite useful because I can do a number of things with this. I can do beat detection, for example. If I know there's a sound of a hi-hat. I mean, in the piece that I'm showing, it's not particularly dance music, but if you were using dance music, you could sample for particular frequencies, and you know that drums have particular frequencies. So you know, like a hi-hat or a bass drum has a particular frequency. So I could just focus in on that area, that bandwidth, and then I could read the values, and from that I could work out how many beats were going on and stuff like that. But within generative art is very much interested in the multiplicity of forms. One of the things about generative art and computers, particularly computers, is a computer will never get bored. It will never get tired of you telling it to do repetitively endless things. So you can tell it to make 100 objects, and then you can map each of those frequencies onto those objects. This is much the same way as a graphic equalizer works. And you can simulate a graphic equalizer quite easily with software by having 512 bands and reading each value. With the amplitude analysis, you have much less information, but in some ways it's more revealing to the environment because you have a collection of frequencies that you're listening to the amplitude of. So you only have one value every 30 frames. But this can be used for much more global transformations. Rather than transferring multiple objects, you might just want to transfer the whole environment, make it brighter, make it duller, make it do various things on a global level, which would be isomorphic in the way that you would perceive the sound. Another aspect of this real-time environment is that I can use these external devices, these MIDI controllers, I can map various attributes within my system and control it. And again, that gives me a little bit of human-machine feedback because I think with this kind of work, it's very important that there's still a performative aspect to it, and it's not just a case of coming in and pressing some buttons and letting these things run in an autonomous way, because then it kind of loses its edge a little bit and it loses its soul a little bit, I think. So I have these MIDI controllers that allow me to control aspects of the performance. So that's a little bit about the performance that I'm going to show you later. I'm just now going to talk a little bit about my research blog. Dataisnature, which I've been running since 2003. It's actually on hold at the moment while I update the database and redesign it. But I've had 3 months out since 2003, and it's been quite a regular posting going on since that time. It set out as a recreational research blog. I call it recreational research in the sense that I was doing this research that was based and revolving around my artworks, because I find that the scientific community would inspire me in many ways. And I found that maybe these annotations and these things that I was finding might be interesting to other communities, art communities, science communities, and whoever was interested, really, because it was very much interested in this dialogue between art and science, which is very much a phenomenon that's blossomed and exploded in the last 10 years. The really kind of crucial bit in early Dataisnature was this idea of algorithmic bridges between art and science. What really impressed me was that on one hand, the artists were looking at the scientific community, and particularly looking at their algorithms and thinking of ways of how they could use those algorithms in an aesthetic sense. So they were taking these well-known algorithms and then they were appropriating them and then changing them, and then in a way they were making them much more interesting to look at than the scientists were. Sorry, I hope I'm not offending you by saying that. But then there was an interesting cross-referencing, because I think scientists were then interested that artists were taking algorithms which were up until then just purely meant to prove ideas. And they were looking at the way that artists were using these algorithms and then borrowing the aesthetics back. So, and this created an interesting dialogue and a mutual appreciation on both sides. And there's 4 examples there, and on the left there are what is perceived as artworks from the intermedia establishment, and on the right are typical scientific visualizations from the algorithms. The first one is a Voronoi algorithm, which is a subdivision in space algorithm whereby you divide up a topology according to points on a plane. And on the left, Robert Hodgkin's I think they're called Voronoi butterflies. He's used them to, in a way, insinuate the patterns, the cellular patterns on butterfly wings, and I think he does it quite well. And going around clockwise to the right, the reaction diffusion equation is a well-known equation for describing the way that 2 chemicals might mix, and the way that essentially if you model these systems you have an activator and inhibitor, and the way that the activator and inhibitor react on each other within this system, you create various kinds of patterns. And this, as an idea, was first proposed by Alan Turing with his famous paper, The Chemical Basis for Morphogenesis. And it essentially describes all kinds of morphogenesis type patterns in nature. The famous classic cases of leopard spots being modelled using the reaction diffusion algorithms. And on the left, nervous systems, LAMP. They used the LAMP, they're a design company, and they used the reaction diffusion to create this 3D form, which has this remarkable textural quality, but also these holes allow the light to come through. It's a shame I didn't have a picture of the actual LAMP in action, but it's quite an interesting thing to see, because obviously these holes allow also a reaction diffusion pattern to be projected onto the externals. The bottom left is using an L system. L systems are these interesting formal grammar systems that describe the branching structures in plants. They're almost like a kind of codified lettering structure, which are kind of recursive algorithm, where they are recursive in the sense that they create these recursive forms. And they were developed by Lindmeyer, and he also has a very interesting book called The Algorithmic Beauty of Plants, which really goes into exploring L systems at great length. Perlin noise. Kern Perlin invented Perlin noise as a CGI prop for creating textures, CGI textures in films. It actually was first used in the film Tron, and he won awards from it. And you can use reaction diffusion equations to create pseudo-random number sets, which then you can apply to elevations and create these synthetic landscapes. And on the left, Eva Schindlins used the Perlin noise algorithm to generate almost essentially what you could say was a drawing machine. It's creating paths, trails based on these pseudo-random numbers. and creates this wonderful kind of drawing system. So the blog kind of spread out quite a bit and ended up being a much broader remit. And here's a list. I'm not going to read through them. Here's a list of all the areas that I've gone on to discuss and talk about. But I believe all of them are connected by two key connections, which is processes and parameters. All of these systems are very much involved in process and parameters and variables to create spatial temporal configurations and manifestations, and essentially they're all about patterns in some way or another. So I think there's a big connection between all of these. But in relationship to the surface tension and the water, I'm going to concentrate just finally a little bit and talk a little bit about some of the earth processes I talk about at Dataisnature. And I divide earth processes up into even another subgroup, which I talk about as metamorphic computations, Eolian computations, and hydrodynamic computations, which are, the third is obviously more interesting for the subject of this lecture. And essentially I see all of these three as kind of similar to generative art in the sense that if we reverse and look back up and tend to look at them as collections of processes and parameters acting out over time, there are quite a lot, the results from them look quite a lot like generative art, and in a sense they are like computational processes. And we can use these metaphors. You could say that metamorphic computations transform one kind of rock into another, and the variables are temperature and pressure. Eolian computations, which is obviously of the wind, the program actively shapes the earth, and the main variable is wind. And with hydrodynamic computations, fluid flow is the primary variable, and erosion and deposition are secondary variables, which create these spatio-temporal forms. And if anyone's interested in or been interested in this idea of pan-computationalism or the universal algorithm, this idea that perhaps we can, if we could reduce all these very, very microscopic interactions, we could actually view them as a computer program. I know Stephen Wolfram is a proponent of this kind of attitude, and Rudy Rucker, who have written extensively on this idea that we can reduce everything back and see these processes as enormously never-ending computer programs. So I'm just going to literally end up by talking about a few examples of what I mean by hydrodynamic computations. This is the Slot Valley in Antelope Canyon, and it's created by yearly monsoons of water which erode the surface and the edges of these canyons. And in a way, I think a metaphor for this would also be, you could see this as a data recording device in the sense that each year the water flows through, and these fluid flows are almost cutting away at a rock in the same way as a groove in a record is cut. In a sense, it's storing a record of the flows. And these systems also, because they're particulate, can be readily simulated with cellular automated systems. So again, there's this idea that everything can be reduced to a much simpler system. The River Lena Delta in Russia, which is like, I think it's the seventh, it's the longest river in Russia, but it's about the 10th longest in the world. There is the critical points in its course where it changes radically, suddenly, without, there's no indication, but suddenly over periods, maybe 500 to 1,000 years, there will be a sudden change in course, and this is because of the way that the local interactions of particles within the system suddenly build up and change the global format of the river. And up until the computational modelling of river deltas using cellular automated systems, this wasn't very well understood. And now these systems can be simulated and shown that the very, very, very sudden occurrences occur in the water flow unexpectedly. The last few that I'm going to talk about are much more microscopic. This is hydrodynamic distribution of trace carbonate materials to create space-time visualizations of geothermal fluid turbulence. And what happens here is you have rivulets and flows of water which carry silicates, and these are deposited. And what happens is the deposition then forms a circuit by which the water flows. So there's this positive feedback, almost a recursive algorithm in the sense that the water then dictates and attenuates the further flow of water, which then builds up and creates these interesting patterns. This is in Turkey. And the Sinter terraces in New Zealand, a similar process occurs, but this has the extra twist of being coloured by these interesting characters of, known as thermophilic bacteria, which also contain photosynthetic pigments, which are generated by their absorption of inorganic materials. So, you know, these surfaces, I'd like to propose to you that you could see them as spatio-temporal data shape recording devices. So I hope that just by firstly showing how in the first slides and hopefully in my performance later that you can simulate water by computational terms, but also in the reverse, if you begin to use the metaphor and look at the hydrodynamic computations within water and the way it changes landscape and the poetic results in terms of generative shapes that it creates, you know, it might sort of give you another perspective on the way that water creates these shapes. Thanks very much for listening.